This is Team 8's project on electronic properties. I am Andie Roux, and presenting with me is Dan Byers and Nick Emanuele. So first we have the electron configuration of magnesium and nickel. For magnesium, here's our electron configuration, and what we can take away from this has two valence electrons in the 3s orbital. We can also shorten this with our noble gas notation. And then here is an electron configuration chart as well. So for nickel, we have two electrons in the 4s orbital. We can shorten this with our noble gas notation. And then here we just have a chart of the electron configuration. You see the outer shell, there's two electrons. Next we have the electron configuration of indium, and it's pretty long, so we can shorten this with our noble gas notation right here. And then we could take away from that, we have two electrons in the 5s orbital, one in the 5p orbital, totaling 3 valence electrons. If you look in this chart here, there's 3 in the outermost shell. Now we have the electron configuration of antimony, even longer, and some key points with this. We have 5 valence electrons in the outermost shell, as you can see in this diagram here, and we can shorten that with our noble gas notation listed right here. So recommended dopants for indium. P-type dopants, we have boron, gallium, or aluminum. It's because they are each a group 3 metal with 3 valence electrons, and they readily accept electrons from the surrounding indium atoms, leaving behind positively charged holes, and these basically move through the material as charge carriers. For N-type dopants of indium, sulfur would be best, because it has 6 valence electrons, and the extra valence electron contributes to the conduction band, creating a higher concentration of free electrons. So essentially, sulfur acts as a donor atom. For antimony, for P-type dopants, we have lead, boron, gallium, or aluminum. Since antimony itself tends to exhibit N-type conductivity, in order to create P-type conductivity, a dopant like lead will create holes in the crystal lattice, allowing for positive charge carrier movement and P-type semiconductors. For N-type dopants, phosphorus or arsenic, these have 5 valence electrons and readily donate extra electrons to the antimony lattice, creating N-type behavior.
When solving for the band gaps of our semiconductor, which is INSB, we're first going to assume that the temperature is 300 Kelvin. The band gap energy is 0.235 electron volts. The thermal expansion coefficient will be 5.8 times 10 raised to the negative 4 electron volts per Kelvin. And our temperature dependencies will be 200 Kelvin. When you plug them into the band gap formula, we find out that the band gap of INSB is 0.131 electron volts. INSB is used within several fields of technology, including thermal imaging applications within mainly photodiodes, sensors in magnetic fields using magnetoresistance, used within infrared technologies, including the Spitzer Space Telescope.
Hello, I will be presenting on the mobilities, concentrations, and electrical conductivities of both free electrons and free holes for our intrinsic semiconductor. So we have INSB, and so before we even get to the question, well, this is the question actually, I have here all our values, all the equations we use. So this will be the conductivity, so conductivity of the electrons, conductivity of the holes, and the equations for them. Separated here. And then we have here this is the mobility of it, which is this constant v, which we got here, over the temperature, which we're going to be using 300 Kelvin for our example, times beta, and that's another constant, which for both alpha and beta, we will just be using 2. Same thing for our electron mobility. If A, and we have our A constant here. And then we have this equation that we're using for Ni, H equals Ni squared root N C and then V, which they'll just kind of cancel out. Exponent of EGKT, G here, and then we have Boltzmann's constant right here. So quite simply, it's just a matter of grabbing all our constants, which I have done here, and plugging them into our things. After plugging into all of the equations, we find that our whole mobility is 4.4 times 10 to the negative 9 meters squared over volts seconds. Electron mobility is 1.44 times 10 to the negative 8 meters squared over volt seconds. Full concentration is 4.27 times 10 to the 17th centimeters to the negative 3. Electron concentration will be 4.27 times 10 to the 17 centimeters to the negative 3. Whole electron conductivity will be 1.29 times 10 to the negative 3 seconds over meters. And finally, electron electrical conductivity is 1.29 times 10 to the negative 3 seconds over meters. That concludes my portion of the questions.